Hey everybody, welcome to my Calculus 1 Exam 3 Review Problems and Solutions video. In this video I go through a bunch of problems, both theoretical and practical, related to both derivatives and integrals. So let's get started. We start with a bunch of true-false questions. Number 1 says, if f prime is always positive for all x in some interval from a to b, then f is an increasing function over that interval. That's most definitely true. It's called the increasing function theorem, in fact. It can be proved with the mean value theorem, which comes up in problem 4 here, increasing function theorem. I should note, however, that the converse of this statement is false, and that's relevant for number 2. Number 2 says, for example, this function is increasing over the entire real number line. Therefore, f prime of x is greater than 0 for all x. Well, you can just compute f prime and see that it's not always greater than 0. F prime of x is 3x squared. That is not always strictly greater than 0. In particular, f prime of 0 actually equals 0, in spite of the fact that the function is always increasing. This is false. Number 3, the function f of x equals x to the fourth has a critical point at x equals 0. That is true. F prime of x is 4x cubed, and certainly f prime of 0 equals 0. But this point is neither a local maximum nor a local minimum, since the second derivative, which is 12x squared, is 0 at 0 as well. That sounds kind of confusing. It's probably best to think about what the graph is. You could use your calculator. The graph of x to the fourth does have this kind of shape to it, kind of parabola-like, though it is extra flat, you might say, near the origin. It's not technically a parabola. However, because the graph looks like this, it definitely has a minimum value at the origin. When x is 0, that's when this function x to the fourth is as small as possible. So saying it has neither a local maximum nor a local minimum is not true. This is a false statement. Number 4, the function inverse sine of x, also called arcsine of x, does not satisfy the hypotheses of the mean value theorem on the interval from -1 to 1, and therefore it also does not satisfy the conclusion of the mean value theorem. You need to know the mean value theorem. What does the mean value theorem say? I'm not going to write it out completely, but you do need, for the function in question, continuity over some closed interval and differentiability over the corresponding open interval from a to b. Does that happen with the inverse sine function for this interval from -1 to 1? If you graph it, it looks about like this. And, well, you can differentiate it and see that the derivative does not exist at the endpoints, -1 and 1. However, those are the endpoints. And in the hypotheses of the mean value theorem, you don't need differentiability at the endpoints. It's good enough to be differentiable on the entire interval except the endpoints. And that happens with the inverse sine function. So the very first part of the statement is in fact false. It does satisfy the hypotheses of the mean value theorem, and therefore it would also satisfy the conclusion. There would be some point, or at least one point, maybe more than one, between -1 and 1, where the slope of the tangent line equals the slope of the secant line. You can see visually that's going to happen. Maybe right about here and right about there. So in spite of the fact that the tangent line becomes vertical at -1 and 1, the function is not differentiable at -1 and 1, it does satisfy the hypotheses of the mean value theorem and therefore satisfies the conclusion. That's false. You could actually also find those values where the tangent line has the same slope as the secant line. All right, number 5, compute this crazy looking derivative, the derivative with respect to t, of the integral from 0 to t of e to the sine of u du. Whoa, that looks crazy. How could this just be a 2-point problem? And hint, in spite of how this looks, it's actually a problem that can be done very quickly, like 5 seconds. What? You serious? Actually, if you know what you're doing, you can do it maybe at 2 or 3 seconds. What do we need to use here? We need to use the fundamental theorem of calculus. In this form, it's sometimes called the first fundamental theorem of calculus, and sometimes it's called the second. It depends on the textbook that you're using. The form of it is that if you differentiate an integral where the variable is in the upper limit of the integration of the integral here, and it doesn't matter what you call the variable of integration here, I'm calling it u, the answer is the integrand function, the little f, but replace u with t. That's the answer, okay? And that's why this is so quick. You just got to know this fact. Differentiating an integral gives you the original function. More precisely, differentiating an integral where the variable is the upper limit of the integral with respect to that variable there gives you the function you're integrating, except go ahead and replace the dummy variable here, u, with the variable you're differentiating with respect to, t. Whoa, that was a mouthful, but I hope you get it. And so all you have to do here is just write down this function here, replace the u with a t, e to the sine of t. That is part of the fundamental theorem of calculus, and it's actually a very significant fact. Okay, that's what makes calculus go, you might say. That derivatives and integrals are inverse processes, inverse operations, you might say, of each other. And even though this function, well, you could probably guess for a long time what you might think an antiderivative of that is, you'd probably be unsuccessful. However, what this fact says is we can theoretically construct an antiderivative using integrals, thinking about signed areas, in fact. That's a mouthful, but the problem itself is actually easy. Number 6 is also related to integrals, but now we use the fundamental theorem of calculus in a form that you're more used to actually evaluate a definite integral. Capital F is sine of x squared. Note that the derivative of that is 2x times cosine of x squared. That would be the chain rule that is being used there. Compute and simplify the answer to the definite integral right here, where now I have numbers in the limits of integration, not variables, like in number 5. So this is the fundamental theorem of calculus in the form that allows you to evaluate the definite integral. This is actually fairly easy as well when you know what you're doing. To evaluate this definite integral, to find the signed area between the graph of this function and the horizontal axis, you need to just do capital F of the upper limit, square root of pi over 2, minus capital F of the lower limit. Capital F is an antiderivative of this function here. I just noted that there. So just do that calculation, okay? In a Calculus 2 course, you would have to do this integral without knowing this right away. You'd have to figure out the fact that capital F is an antiderivative of this function right there, and then do this. Here in a Calculus 1 course, I'm helping my students a little bit more by telling them what an antiderivative is here. And so you just go ahead and plug these numbers into sine of x squared. So I need to square this square root, and so the square root goes away. And when I plug in 0 into that function, I get also sine of 0 squared, which is still sine of 0. Sine of pi over 2 is 1. Sine of 0 is 0. This is 1. The final answer is 1. On to the next problem, an abstract problem using properties of integrals here. We're supposing that the integral of a given function f from -2 to 3 is 11, and of another function g from -2 to 3 is -4. Find the integral of this linear combination of those two functions. That's just a matter of using properties of integrals. Integrals like this are linear. You can factor out the constants, and you can also separate the integral of a difference into the difference of two integrals. And what that means is you can write this as 4 times the integral from -2 to 3 of f minus 8 times the integral from -2 to 3 of g. Okay, that's a linearity property of integrals. That's what you need. And you also need the given information that the integral of f from -2 to 3 is 11, and the integral of g from -2 to 3 is -4. It is important that the interval of integration in each of these integrals is the same, -2 to 3. So this becomes 44 plus 32, and that will be 76. Okay, so the answer is 76. It's an example of using abstract properties of integrals. Other kinds of problems where you might have to use abstract properties of integrals include problems where the functions might be assumed to be even or odd functions, and you need to use symmetry if the interval of integration is symmetric about 0, like from -2 to 2 instead of -2 to 3. So look for those kinds of problems as well. Number 8. Let g of x be natural log of x plus 1 and h of x be 2x. These are continuous functions. Their values at 0 are both 0, and therefore this limit is what's called a 0 over 0 indeterminate form. Okay, I'm giving my students some help by saying all these things. The directions say to use L'Hopital's rule to calculate the limit. Okay, so I'm helping my students by telling them what to use to just try to help them not get things wrong. But you might have a problem where your teacher doesn't tell you what to do, and you need to recognize, hey, this is a 0 over 0 indeterminate form. I cannot evaluate the limit by just plugging in 0. And in fact, you might think because you'd be dividing by 0 when x is 0, that maybe this function has a vertical asymptote at x equals 0. But it actually doesn't because the top approaches 0 as well. So we need to use L'Hopital's rule in that kind of situation when you have such an indeterminate form. There are other kinds of indeterminate forms as well. If L'Hopital's rule does not apply, then don't use it because you'll get the wrong answer. But this is a situation where it does apply. And what does it say to do? It says to compute a new limit of a new fraction where the numerator, the top of the new fraction, is the derivative of the old numerator. The derivative of natural log of 1 plus x would be 1 over 1 plus x times 1 from the chain rule, divided by the derivative of the original denominator. The derivative of 2x is 2. This is not the quotient rule, okay? Don't ever think that L'Hopital's rule involves the quotient rule here, in this kind of context at least. It does not. I don't need the quotient rule for either the derivative of the numerator or denominator. So it's the derivative of the top divided by the derivative of the bottom is the new fraction that you compute. And sometimes you actually have to use it more than once. We might have to use it again, or maybe even 3 times, okay? Is this an indeterminate form? If it is, use it again. If it's not, then don't use it. Just evaluate the limit straight away. This is not an indeterminate form anymore. The top approaches 1 over 1, 1. As x approaches 0, and the bottom is constant. It stays at 2. So the answer is 1/2. There we go. And if you don't believe it, or you're not sure, you can always use your calculator to graph this function. Just double checking things. Natural log of 1 plus x divided by, talking about the original function here, 2x. I want to plot this near 0 and see if it seems to be approaching 1/2, and that would give me confidence that I did it right. So let x go from -1 to 1, say, and y go from maybe -1 to 1 as well. And let's take a look at the graph. It does look like it's approaching 1/2, and you could use the trace feature to try to see if that's the case. Yeah, when x is close to 0, y is close to 1/2. Technically, when x equals 0, the function is undefined, so really there would be a hole in the graph at x equals 0. But of course, the calculator is just plotting points and connecting the points, so it doesn't know that. You know that. There's a hole in the graph, but the limit does exist. On to the second page. Second page includes 2 problems that are related to optimization. Once again, partially to give my students help and partially to make grading easier, I give them some help on some things here. But your teacher may not. So I got a function here, a cubic, and there I'm telling them the derivative. Okay, that's fairly easy to do, but I'm trying to also emphasize you can factor the derivative like that. The point is to use the first and second derivative test here. That's what I'm really testing here. Part A says to state all the critical points of f, just the x-coordinates. Sometimes people include the y-coordinates as part of a critical point. Briefly show, work, and explain. Part B, make a number line, test the sign of f prime to use the first derivative test for local maxes and mins. And we'll also in part C confirm answers with the second derivative test, and then in part D find max and min values. That means outputs or y-coordinates. All right, part A, state all the critical points. The critical points in general are where your function has a derivative equal to 0 or a derivative that's undefined. With fairly simple examples like polynomials like this, it's going to be where the derivative is 0. So f prime of x, if I set that equal to 0 and solve for x, well, there is the derivative. And the only way this product is going to be 0 is if either x minus 3 is 0 or x plus 2 is 0, which means your critical points are positive 3 and negative 2. Okay, so there's the answer to part A. Part B, make a number line, test the sign of f prime at various spots. What does that mean? We'll have to get into it. Show how to use the first derivative test to classify the critical points as local maxes or mins. So make a number line. What you do is you mark off the critical points, -2 and 3. And to test the sign of f prime, what you do is you pick points in between the critical points, and well, or to the left and right of the most extreme critical points. the two critical points here break up the number line into 3 intervals. You need to use test numbers in each of these intervals to decide whether f ultimately is increasing or decreasing based on the sign of f prime. You're also implicitly using the continuity of f prime when you do this, but that's certainly the case in this situation. So I could compute f prime, for example, of -3. I could actually find its value, but you actually don't have to find its actual value. You can just decide on its sign. Plug it into the factored form. 6 times -3 minus 3 is a negative number, times -3 plus 2 is another negative number. Positive times negative is positive. So the derivative is positive when x is less than -2. So f is increasing when x is less than -2. You're again also using the continuity of f prime when you say that. Test a number in here, like how about 0? F prime of 0. Imagine plugging 0 in here, I get positive times negative times positive. This is negative. So that means f is decreasing, the increasing and decreasing function theorem, just like on number 1. Test a number over here, like 4. Positive times positive times positive. This is positive, so f is increasing again. Of course, f is a cubic with a leading coefficient that's positive, so that also confirms this has got to be the way that the graph is ultimately looking, going up, then down, then up again. And that means by the first derivative test, which I won't state completely, that means that you have a local maximum at x equals -2, local max at x equals -2, and a local min at x equals 3. You can see it in the graph. I'm imagining to draw the graph. Function goes up, then down, then up again. If the derivative is positive, just to the left of a critical point, and negative just to the right, then that's going to be a local max. If it's negative just to the left of a critical point and positive just to the right, then you're going to get a local min. You can imagine the graph again. Okay? On to part C, we're confirming the answer to part B by using the second derivative test. The second derivative test tells you whether you have local maxes or mins based on the sign of the second derivative at the critical point. And again, technically the continuity of the second derivative is relevant as well. What is the second derivative here? Well, okay, I didn't tell my students this one, but let's go ahead and find it here. Look at the first derivative in this form. You can see the second derivative is going to be 12x minus 6. Plug the critical points into the second derivative. F double prime of -2. I won't bother calculating it. It is going to be a negative number. That means f is concave down near that critical point, and you got a local max. It's like the top of a hill. Local max at x equals -2. F double prime of the other critical point, 3. Plug in 3, you get 36 minus 6 is 30, is positive. So that means the graph of f is concave up near that critical point, and you have a local min. This is like the bottom of a valley there. Local min at x equals 3, confirming our answers to part B. Part D, find the local max and local min values, outputs, y-coordinates of f at the critical points. So a local max value, emphasis on the word value, that's what I say for the outputs, is f of x equals -2. The value of x, the critical point where you have a local max. Okay? So that's f. I need to go back to the original function, not the derivative or the second derivative, back to the original, and compute f of -2. So I get 2 times -2 cubed is going to be -16, minus 3 times -2 squared is going to be 3 times +4 is 12, so minus 12. Minus 36 times -2 is plus 72. Plus 5, so this is 77, this is -28, and so it looks like we get 49 here. Hopefully I've not made a mistake. I'll try to make a note if I did make a mistake. And the local min value is f at the critical point. That is where the local min occurs, 3. Plug in 3 up here. 3 cubed is 27 times 2 is 54. Minus 3 times 3 squared is minus 27. Minus 36 times 3 is minus, what would that be, 108? Plus 5, that's a 27 there. This is a negative 103, and so we get negative, what would it be, 76? Is that right? Hopefully I have not made arithmetic mistakes here. Yeah, I think these are right. Local max value and local min value. Again, if I make a mistake, I'll make a note on the video. Number 10 is, oh, by the way, so this is first and second derivative test for local extrema. If you also need to optimize a function over a closed interval, so you've got to include the endpoints, you actually have to test the value of the function at the endpoints if you're after what are called global maxes and mins. Another comment is local max and mins. Another name for that is relative max and mins. And another name for global is absolute. So just some comments there. Number 10. Consider the two-parameter family of functions like this, where a and b are parameters, constants, x is the variable, though what's most interesting is to ask what happens if those constants change, which sounds oxymoronic. How can constants change? Well, they can change in your mind if you want them to change, okay? And that is what's most interesting about this kind of thing. We are focusing on positive values of x as well. Part A, show calculus and algebra work to confirm the positive critical point of this function is at this value of x. It depends on a and b. And so you can even think of it as a function of a and b. I use this kind of notation, x sub crit of a and b. This is the x coordinate of the positive critical point. Okay. Well, how do you do that? Just same as the previous problem, just take the derivative, set it equal to 0, solve for x. Okay, I didn't tell them the derivative of this one, so okay, that's going to be a little bit more work, say, but it's not too bad. Look at it in this form. The derivative of ax with respect to x is a, and the derivative of plus bx to the negative 1 will be minus bx to the negative 2. There is the derivative, which can also be written as a minus b over x squared. When you do this work, you need to think of a and b as fixed. X is the variable, though again, ultimately, we could also imagine what happens as a and b change. We could even use multivariable calculus to find partial derivatives of this with respect to a and b to try to analyze how the critical point changes when a and b changes. And that's pretty interesting, but it's not a part of this problem. Set this equal to 0 and solve for x. You could rewrite this as a equals b over x squared. Then you can cross multiply effectively, multiply both sides by x squared and divide both sides by a. And we are after the positive critical point here. So now just take the positive square root of b over a, or if you prefer, b to the 1/2 times a to the negative 1/2, and that does confirm this answer right there. I'm just calling it x here, and that's fine. It's just here that I called it x sub crit of a comma b. Part B, use the answer from part A and show algebra work to confirm that the minimum value, and it is going to be a minimum, part C is to confirm that, is this y coordinate. This thing right there. I'm calling it y sub min of a and b, so I could think of it as a function of a and b and analyze it. How does it change as a and b change? We use partial derivatives, but you don't have to. It's not part of the problem. Well, it's just a matter of plugging this critical point here into the function f itself, the original function again. So plug in this thing, and I think I'll use it with the exponents there, b to the 1/2 times a to the negative 1/2 into the original function, say in this form. I get a times x, a times b to the 1/2, a to the negative 1/2, plus b times x to the negative 1. So I get b to the 1/2, a to the negative 1/2 to the negative 1. Use properties of exponents. You can add the exponents here. A to the first times a to the 1/2 gives you a to the positive 1/2 times b to the positive 1/2. And then with this one, first distribute the minus 1 through here and multiply times those exponents. So I get b to the negative 1/2 and a to the positive 1/2. Add those exponents, you get a b to the positive 1/2. This simplifies to a to the 1/2 times b to the 1/2. So I've got two terms that are the same, and I'm adding them, so I get 2 times a to the 1/2, b to the 1/2, which can also be written as 2 times the square root of a times b. And that is confirming what you see right there. Okay? Part C, compute f double prime and use it to briefly explain why the answer to part B must be truly a minimum rather than a maximum. Or maybe neither. Neither can occur as well, right? I didn't mention that before. Sometimes with critical points, it's neither a max nor a min. What is f double prime of x? Use f prime there. The derivative of a is 0. The derivative of this part is going to be positive 2bx to the negative 3, which is the same as 2b over x cubed. And the relevant thing about this is positive for all x that are positive. It's not only positive at the critical point, so locally near the critical point your graph is concave up. In fact, it's concave up for all positive x. And that's enough to say it's definitely not just a local min, but even a global min, you might say, when x is positive, because this second derivative is concave up. The graph of the function has got to have this kind of shape. And you can double check that on your calculator if you use fixed values of a and b. Okay? Got a global min right there. This would be x crit and of a comma b. And this second coordinate would be y min of a comma b if I want to use the notation from before. Okay? All right, on to the next page. The velocity of a particle along a straight line in feet per second, sorry, I probably should have used meters per second, is given by this function. That's the velocity. And this function takes on both positive and negative values, okay? The velocity could be positive or negative at various times. You could be moving to the right, say with positive velocity, or to the left with negative velocity. Using the fact that this function, capital F, is an antiderivative of little f, though it's not necessarily the position, because you don't know the initial position, show work to find the change in position of the particle from time 1 to time 3, including units. Yes, this function could be the position function, although it only would be if your position at time 0 is 0, because this function's value at 0 is 0. Okay? However, that's irrelevant. The integral is going to give you the change in position, whether this is the actual position or not. The change in position is going to be given by the integral of the velocity, little f of t, over whatever time interval you're talking about. In this case, it's time 1 to time 3, which I can certainly go ahead and write like this. And by the fundamental theorem of calculus, since this capital F is an antiderivative, this is going to be capital F of 3 minus capital F of 1. Okay? Again, capital F could be the position function if your position at time 0 is 0, but it doesn't have to be. The change in position still equals the change in f, really. If f is the position, that is the change in position. But it still gives you the same answer either way. So plugging in the numbers, 5/2 times 3 squared is times 9, minus 1/4 times 3 to the 4th is times 81. That is f of 3. F of 1 is going to be 5/2 minus 1/4. All right, so we're going to get, let's see, 45/2 minus 5/2, and also a minus 81/4 plus 1/4, right? The two negative signs make a plus. So this becomes 40 over 2, which is 20, and minus 80 over 4, which is also 20. Answer is 0. Whoa, is that an accident? Well, if I haven't made a mistake, no, it's not an accident. The change in position is 0. This particle is moving. It's moving back and forth from time 1 to time 3. It ends where it started. The ending position at time 3 is the same as the starting position at time 1. Okay? Let's just double check this with the calculator. Go to my function window here, plug in the velocity function. 5, of course, you got to use an x on the calculator. 5x minus x cubed. Okay, so there's my velocity function. I'm going to plot it over a window bigger than 1 to 3. I'll plot it from 0 to 4, say. Window from x goes from 0 to 4. And how big does this function go? I'm not sure. Let's try negative 10 to 10 just to see what it looks like here. It's positive velocity there, then negative velocity. From 1 to 3, there's some positive values of velocity, some negative. The object, the particle, is moving to the right, say, at first, and then to the left. Do these areas cancel each other out? Evidently they do, if I have not made a mistake. Let's go ahead and calculate the integral from a lower limit of 1 to an upper limit of 3 and see if we do get, in fact, 0. And yeah, that is 1.2 times 10 to the negative 13. That's rounding error to 0. The answer truly is 0. These areas cancel each other out for the definite integral. Okay, so the object ends where it starts. Okay, that's the way it turned out. It didn't have to. It could have been positive. It could have been negative. If it were positive, it would end to the right of where it started. If it were negative, it would end to the left of where it started. Number 12 is a related rates problem. A 5-meter long ladder is leaning against a vertical wall. So here's the wall. Say here's the floor. And here's our ladder. It is a fixed length. This is 5 meters. Hey, I'm using meters. How about that? The bottom of the ladder slides away from the wall at a rate. Related rates. Rate of 0.2 meters per second. How fast, what's the rate, is the top of the ladder sliding down the wall when the bottom of the ladder is 3 meters from the wall? Note, it's going to be sliding down, so the rate of change of the vertical distance is going to be negative, but the answer is positive since you're being asked how fast is it sliding down. We're saying it's sliding down, so we're after the absolute value of the rate of change, really. Okay, some teachers may not emphasize that, but I am emphasizing that. So what do you need to do? So again, the ladder is a fixed length, 5 meters, but it's sliding. This is going down as this goes to the right. It stays on the floor and the wall. It's not jumping or anything. Call this distance x and call this distance y. X and y depend on time. They are changing over time. X is getting bigger over time and y is getting smaller over time. They are changing, and they are related to each other. This is a right triangle. The Pythagorean theorem can be used to say that no matter what time you're at, x squared plus y squared equals 5 squared, or 25, for all t. Okay, you don't see a t in this equation. It's understood that both x and y depend on time. You know, in general, you see something like this, you would not assume that, but we are assuming it here for this practical situation. And what you then do is you differentiate both sides of this with respect to t. d dt, treating x and y as functions of time. If you prefer, you could write an x of t in there and a y of t in there. That's fine to do. It's not traditional, but it's fine to do. You need to use the chain rule. X of t quantity squared is x squared is like x of t quantity squared. There's an inside function and an outside function, the inner function being x of t and the outer function being the squaring function. So you need the chain rule. You'd bring down the 2 to get 2x, or 2x of t, and then multiply times the derivative of x with respect to t. You could write x prime, but to emphasize the variable is t, I'm going to go ahead and write dx dt. Do the same thing for y, which also depends on t, and you get a similar kind of thing. The 25 truly is a constant. Its derivative with respect to t is 0. What am I after? I'm after knowing dy dt and ultimately its absolute value. When I know dx dt, it's sliding away from the wall at 0.2 meters per second at a certain moment in time. That's not necessarily a constant rate, but at a certain moment in time, that's the case, or maybe it is assumed to be a constant rate. Okay, I guess it's sort of assumed to be a constant rate, but that doesn't mean dy dt is constant. So you need to solve this equation for dy dt in terms of dx dt. Well, the 2's cancel. You can write y times dy dt equals negative x times dx dt. And dividing everything by y, that's going to imply that dy dt in general is negative x over y times dx dt. So do the differentiation, and then only at the end plug in your numbers. We can replace dx dt with 0.2, and we can replace x and y with where they are at the certain moment in time. When the bottom of the ladder is 3 meters from the wall, when x is 3, I'd plug in x equals 3. What do I plug in for y? I need to use the Pythagorean theorem again. I need to use the fact that this is true no matter what t is. So y is going to be ultimately square root of 25 minus x squared. Square root of 25 minus 3 squared is 9, is square root of 16 is 4. So I ultimately get negative 3/4 times 0.2 when I substitute the numbers in. Only do that at the end, okay? Differentiate first, then plug the numbers in at the end. So this will be negative 0.75 times 0.2. What would that be? Negative 0.15? I'll just double check things. I'm afraid I'm going to make mistakes here. So 3/4 times 0.2. Yeah, 0.15 with a negative sign. But that's not the final answer. The final answer is right over here, the absolute value of dy dt, because I'm saying how fast is it sliding down, because I got the word down in there. So this is going to be 0.15. Units would be meters per second. Okay, that would be the final answer. Okay, and even if dx dt is constant at 0.2 meters per second, even if that's always 0.2, the fact that x and y change means dy dt is not constant. Okay, that's kind of interesting to think about. All right, another interesting thing to think about is that as y approaches 0, this approaches infinity, which would mean this is moving faster than the speed of light. Boy, I guess that's where the mathematical modeling doesn't work so well. Next, we have a practical optimization problem. The volume of a closed cylinder is fixed at 10 cubic centimeters, so that we can relate h and r, the height and the radius, by this equation. This is called the constraint. The goal is to find the dimensions of r and h, the radius and the height, that minimize, make as small as possible, the surface area, which is given by this quantity. Let's draw a picture quick just to see that that makes sense. So a cylinder is this kind of shape here, like a can. It's got a certain height, h, and a certain radius, r. The top and the bottom of the cylinder are circles, each with area pi r squared, and there's 2 of them, so that's 2 pi r squared for the surface area of the top and the bottom. The circumference of the circle at the top or the bottom is 2 pi r. If that gets multiplied by h, then that is going to be the surface area of the sides of the cylinder. This is calculus 1, so we need to be able to write the surface area as a function of just one variable, not multivariable calculus. So we can use our constraint, we can use the h, and replace the h in this expression with what you see here to get a function of r alone. That's the surface area as a function of r, and that's the function that we want to minimize. So the formula ultimately becomes 2 pi r squared plus 2 pi r times h, but h gets replaced by 10 over pi r squared. Go ahead and cancel those pi's. Go ahead and cancel one of the r's, leaving you with 2 pi r squared plus 2 times 10 is 50. We are left with also an r on the bottom, which is the same as doing 50 times r to the negative 1 power. So that's the surface area as a function of r. R must be positive. We're trying to find really the global minimum value of this. Where does that occur, what radius, and we can then also figure out the corresponding height. So we need to differentiate this to get 4 pi r minus 50 r to the negative 2, which you can write as 4 pi r minus 50 over r squared. Set this equal to 0 and solve for r. You can write this as 4 pi r equals 50 over r squared. We can multiply both sides by r squared and divide both sides by 4 pi to get that r cubed is 50 over 4 pi, or if you prefer, 25 over 2 pi. Therefore, it looks like the radius that gives us the minimum surface area is going to be the cube root of 25 over 2 pi. Let's go ahead and approximate what that is. In trouble here. 25 divided by 2 pi. And then raise that to the 1/3 power, that's the same as the cube root, gives a radius of about 1.585. And what are the units? The units are going to be, in units of distance here, is centimeters. 1.585 centimeters is the radius that evidently gives the minimum surface area. What's the corresponding height? Go ahead and use the constraint again. 10 over pi times r squared. H is 10 over pi times r squared. So I need to plug that number in for r squared, in for r, meaning I need to square it, then multiply by pi, and then take that number, divide it into 10. So 10 divided by this number. And the corresponding height is about 1.268 centimeters. Okay, so those would be the dimensions, the radius and the height of a cylinder with a fixed volume of 10 cubic centimeters that gives us a minimum surface area. We didn't actually find what the minimum surface area is. If we wanted to do so, we would take these numbers and plug back into this equation. I won't bother doing so. We do not need to prove that S is minimized. It will be. You could use the second derivative test. It's fairly quick actually to do so. The second derivative ultimately is positive. When r is positive, the graph ends up looking about like this. And it's kind of like the other problem. We are minimized with a graph that looks about like that. But this is the answer. On to the next problem. 14 is a differential equations problem. Maybe you talk about differential equations in your Calc 1 course, maybe you don't. Whether you do or not, this is a fairly easy problem. Show work to verify this function is a solution of this differential equation, though it's a little confusing, okay? What you need to do is just plug the function into both sides, the left-hand side and the right-hand side, and simplify and see if you get the same thing. So the left-hand side, LHS, and this is true in general for differential equations, is dy dx. And for this function, that simplifies to 2x. And the right-hand side is 2y over x. And for this function, that's 2x squared over x, which, at least if x is not 0, simplifies to the same thing. And we won't worry about what happens when x is 0. These are the same. So that means we've done it. That's a solution of that differential equation. Now, technically, you might say this does not apply when x equals 0, but we're not going to worry about that kind of technicality. X squared is special. Other functions would not solve it. Like, you know, if f of x were x cubed, then dy dx would be 3x squared. I think x cubed is not going to solve it, but I'm not sure, actually. And then 2y over x would be, plug in x cubed, is 2x cubed over x, which was simplified to 2x squared. Not the same, not the same. They are equal when x is 0, for example, but they're not the same functions, so x cubed does not solve the differential equation, and you should be able to verify something like that as well. Okay, so it's really not that hard. You just got to know what to do. Plug whatever function you're talking about into both the left-hand side and the right-hand side. Find dy dx, replace y with the function, and see if it simplifies to the same thing. And again, we're not worrying about domains here. 15 is also a problem that you may or may not have in your Calculus 1 course. You might be more likely to have it in a Calculus 2 course, but I like introducing it in Calculus 1. This function, this linear function, is, in this application, something I'm going to call a density function for modeling data when x is between 0 and 10. This is about data modeling. You can also relate this to probability as well. Part A just says, where is the data most dense? Well, what does this mean? What's this all about? Let me go ahead and explain it to you. If you graph this density function, it's going to be a straight line with a y-intercept of 1/5, 0.2, and a slope of negative 1/50th, negative 0.02. Do notice that when x is 10, if you plug in x equals 10 into this, you are going to get 0. So when x is 10, the function goes down to 0. So the graph looks something like this. That's what the graph of little f of x looks like. as a density function, and this applies not just to data, but it actually applies to physics too. If this is representing the density of data or the density of, say, a thin rod of metal or something, where the graph is higher, that's where it's most dense, okay? So the data would be most dense where this graph is highest, near 0, and lowest, near 10. If it were representing the density, the mass density in, say, grams per centimeter, a linear density of a thin rod, it would be most dense where the graph is highest, near 0, and least dense where the graph is lowest, near 10. So as far as part A goes, it's just your choices are low values of x, near 0. Okay, that's the answer. Part A, the answer is 1, low values. Not medium-sized or not large values. Part B, this function is called the cumulative distribution function. Notice it's an antiderivative of little f. The notation is suggestive. Not any old antiderivative, not with a plus c here, but a particular one, whose value at the left end point of the domain here at 0 is 0, in fact. That is enough to make it a cumulative distribution function. And what does that mean? Well, evidently it's going to help us find the approximate percent of the data less than or equal to, for example, 5. Density functions have to integrate to 1. This problem's not asking about that, but this has to integrate to 1. The area under this has to equal 1. It's a triangle. The area, 1/2 base times height, 5 times 0.2 is 5 times 1/5 is 1. That's something that density functions have to satisfy. Effectively, that represents 100% of the data, or in probability terms, it represents 100% of the probability. The approximate percent of data less than or equal to 5, it turns out, is going to be the integral of this density function up to 5, from 0 to 5. And that's going to be bigger than 50% here, bigger than 0.5. Most of the data are going to be close to 0, less than 5 certainly. Most of the area under the graph is less than 5, when x is less than 5. So the answer is going to be the integral of little f from 0 to 5. And then you could convert it to a percent. You're going to get a decimal answer. By the fundamental theorem of calculus, that's capital F of 5 minus capital F of 0. We did note that capital F is an antiderivative of little f. Capital F of 5, 1/5 times 5 minus 1/100th times 5 squared. Capital F of 0 is 0 minus 0 is 0. So this becomes 1 minus 5 squared is 25. 25 over 100 is 75 over 100, or 3/4. 0.75 as a percent, that's 75%. So 75% of the area under this graph over this interval from 0 to 10, for x less than 5, that's 75% of the area. It's also 75% of the data. It's also 75% of the probability. It is an approximation in terms of data modeling, because data modeling involves randomness, and so you won't necessarily, if you do a random sample of size 100 or something from this data set, you won't necessarily get exactly 75% of the data being less than 5. But as a model, a good model, hopefully it should be close to 75%. 16. Parametric equations. This parameter t is not a constant. It's not like that problem with the a and the b. This is x is a function of time, say, and y is a function of time going from 0 to 2. Time is in seconds, distance is in meters. This is motion in the plane. X and y both depend on time. Part A, use your calculator to help you draw the parametric curve defined by these parametric equations on the set of axes here. Include the direction of motion as t increases. In other words, draw an arrow on the curve showing you how it moves as t increases. Let me plot a few points and I'll confirm it with the calculator. You can just make a little table here. Say t is going from 0 to 2 maybe, so maybe I pick 0, 0.5, 1, 1.5, and 2. What are the corresponding x and y values? Well, x equals t, so x is the same as t. Y equals t squared, so I need to square the t to find the y coordinates. 0 squared is 0, 0.5 squared is 0.25, 1 squared is 1, 1.5 squared is 2.25, and 2 squared is 4. Plot those points, the x and y coordinates. 0, 0. 0.5, 0.25 would be, what, about here or something? Oh, right about there. 1, 1. 1.5, 2.25, right around here. And 2, 4. And you're going in this direction as t increases. So if I draw this, I'd want to draw an arrow on top of it. Okay? If you wanted to confirm it with your calculator, you'd want to be in parametric mode, par, like that. And you'd want to plug in these functions. X is t, y is t squared. Into your window, let t go from 0 to 2. X in this picture is going from 0 to 5, say, and well, let's go 0 to 5. And y goes from 0 to 5 in the picture as well. Graph it, and there it is. And it is getting traced out in the direction of motion. You could reverse the direction of motion here and it would get traced out in the other way. I won't bother with that, but that's something that could be done. Sometimes I also ask my students to draw position vectors and velocity vectors here at time 2. I'm not asking this, but I'll go ahead and draw it anyway. Vectors are arrows, and a position vector goes from the origin to the location of the object at the given moment in time. It looks like that. And a velocity vector, you draw an arrow at the location of the object. It points in the direction of motion, instantaneous direction of motion, which would be tangent to the curve here and look about like this. And its length is equal to the speed. I'm not figuring out the speed here, so I don't know exactly what that is. Actually, I can figure it out because I'm telling you what the speed is. At t equals 2, I guess I could go ahead and compute it here. When t is 2, you get 2 squared is 4 times 4 is 16 plus 1 17. Squared is 17 is a bit bigger than 4, so I'd have to make an arrow a bit longer than 4 units there for it to be the true velocity vector, so it'd be a bit longer there. Anyway, I'm not asking that in this problem, but I do sometimes for Calc 2. Part B says show work to confirm that this is the speed. Okay, so this is part A here, this green graph. Part B, you need to just know the formula for the speed. It is the length of the velocity vector, which you can find from the Pythagorean theorem, and ultimately it is the square root of dx dt squared plus dy dt squared, or if you prefer, f prime of t squared plus g prime of t squared. That comes from the definition of the velocity vector, you might say. Though you might wonder, why does the velocity vector have components f prime and g prime? I won't get into that. If you don't know about the vectors, then don't worry about it. But we do need to find f prime and g prime. F prime, there's f of t is t, so f prime is 1. G prime is 2t. So I simplified to square root of 1 plus 4t squared, which is what I said the answer was. Okay, right there. That is the instantaneous speed, rate of change of distance with respect to time at any moment in time. And it changes over time and it gets bigger, so this object is accelerating as well. Part C. Do one of two possibilities to estimate the distance traveled, which is the integral of the speed. Either use your calculator's integration capability, and round your answer to 2 decimal places, or do the right-hand Riemann sum using delta t equals 0.5, this picture, down here can help you remind you what a right-hand Riemann sum would look like. It would be the sum of the areas of these rectangles, where for each subinterval, the height of the rectangle is determined by the height of the function, the speed, at the right endpoint. So for the first subinterval from 0 to 0.5, the value of the speed at 0.5 is up here. Make a rectangle with that height. Same thing for the other subintervals. Okay, let's do it both ways. So first thing I'm going to do is go back to regular function mode. So go to my mode, go back to function, because I need to integrate a function. That's why I'm doing this. And the function I want to integrate is square root of 1 plus 4t squared, which of course I've got to type now with an x in there. 1 plus 4x squared. The window is from 0 to 4. How high does this function go? I don't think it goes above, no, 0 to 2, excuse me, for x, which is the same as for t. Yeah, it doesn't go above 5. So here's the graph of the speed. Same graph that I had down here. And use the calculator's integration capability. I can just do this. X goes from 0 up to 2, which really means t goes from 0 to 2. Get the area out into the graph. As the distance traveled, it's going to be approximately 4.65 meters, right? Units of distance are in meters. So the integral from 0 to 2 of the speed from the calculator turns out to be about 4.65 meters. If you did a right-hand sum, if you did it that way, it's not going to be as precise of an answer. And it's going to be too big, in fact, because you can see the function's increasing, so these rectangles are all above the graph, and the area under them is too big. So the answer is going to be too big, but I did give them that option as another way to estimate the answer. So we need the value of speed at the right endpoints here. Speed of 0.5, plug into the speed function right there. T squared, 0.5 squared is 0.25, times 4 is 1, 1 plus 1 is 2, square root of 2, about 1.4, square root of 2, 4142136 should be good enough. Speed of 1, plug in 1 there, you get square root of 5, about 2.236068. These are in meters per second. Speed of 1.5, 1.5 squared times 4 plus 1 is square root of 10, so you're going to get square root of 10. Square root of 10. About 3.162278. I'm using more decimals than I need. Speed of 2 squared, again, square root of 17 ultimately. About 4.123106. These are the heights of these rectangles. Multiply them times the base, which for each rectangle is 0.5, and you're going to get the area of each rectangle, and then you add those up, which effectively means I can just add these numbers, then multiply by 0.5. So that's what I'm doing here. Times 0.5. Right-hand sum is going to be approximately 5.47 meters. Obviously too big. The calculator's integration feature gives a better answer of 4.65. Okay? But I'm telling my students they can do that. Can this integral be evaluated exactly? Can you integrate this exactly? Yes, but it's not so pleasant. Okay? That's a Calc 2 subject for sure. This is the last page. 2 more problems. The graph below shows the net flow rate dV dt equals R of t in gallons per minute. I should have used liters per minute perhaps, but I use gallons, sorry. water into the tank. A positive flow rate means the tank is filling up. A negative flow rate means the tank is emptying. I'm telling my students, though they shouldn't really know this, this integral is going to represent the net change in volume. Just like the integral of the velocity is the change in position, the integral of a flow rate, water flowing into and out of a tank, is going to be the change in volume. Flow rate is in gallons per minute. The volume would have to be in gallons. Also, the change in volume would have to be in gallons. From time 0 to t minutes, where t is not specified. I could have picked a number here, but I'm not specifying it. I'm saying this is true in general. The u here, just like before, is a dummy variable. Doesn't mean anything. Part A. What is the change in volume from time 0 to time 4? What is the value of this integral if you replace t with 4? No formula here. You got to think conceptually. This is a graph of the flow rate. R of t or dv dt, however you want to think of it. The integral, you got to think in terms of areas. Is this area minus this area? Okay, because the graph is above the axis here and below the axis there. So the answer to A for the change in volume is the integral for the function from 0 to 4. And if I'm putting a 4 up there, it doesn't matter whether I use a u or a t here. I'll use a u. And that, by this picture, is 9 minus 5, which is 4 gallons. The tank is filling up at first from time 0 to time 2, and then it's emptying from time 2 to time 4. But more goes in than goes out because this area is greater than that area. I could have made it so this area was greater, and so then the net change in volume would be negative, though if that were the case, the tank could not start out empty. It'd have to have something in it to start with. Part B adds a little bit more. Suppose the initial volume is 2 gallons. What's the volume at time 4? That doesn't even require calculus. The value of the volume at time 4 is the initial volume plus the change in volume. The initial volume is 2. The change in volume that we just found is 4. So the ending volume at time 4 is 6 gallons. So part A is about change in volume. Part B is about actual volume. No formulas here, just concepts. I told them the areas here. If I did not, I could make it more work by trying to just estimate the areas with maybe left-hand sums and right-hand sums, or perhaps by counting boxes. Each of these boxes has an area of 1. There's 1 minute for that side and 1 gallon per minute for this. The scales are not the same. The product of those two is 1 gallon. 1 gallon per minute times 1 minute. The minutes would cancel and give you 1 gallon. So you could think of each box, each rectangle here, as representing 1 gallon of volume and count approximate boxes to see this area is approximately 9 and this area is approximately 5. And then once again, for the part A, do 9 minus 5 to get 4 or something close to that. Last problem. Theoretical problem. It's a proof. Suppose f and g are two functions that are continuous and differentiable for all x. Satisfy these conditions. Directions say use the chain rule, the constant function theorem, which I haven't mentioned yet, and assumptions to show that this function defined by that equation equals 1 for all x. Whoa, what a weird problem. What's going on here? First of all, what is the constant function theorem? The constant function theorem says that if a function is continuous and differentiable, say everywhere, for example, and its derivative is always 0, then the function must be constant. Okay, so evidently we need to differentiate this function and show the derivative is always 0, and that's where these assumptions are going to come into play. And that would mean it's a constant function. Why is the constant 1? Well, I guess these two assumptions must be relevant. So that's a real quick big picture of what's going on. I also want to say that these functions are actually particular functions that have names. You may not be familiar with them. They're called hyperbolic functions. Turns out that f of x is the hyperbolic cosine function, written cosh of x, C-O-S-H of x, and the g of x function is the hyperbolic sine function, or sinh, S-I-N-H of x. I'll let you look into that if you want, but that's sort of what's going on in the background here. How do you start a proof? Well, proof should be written in complete sentences, so I'm starting them off here. Let h be a function defined by this formula. That's the first sentence. You can have symbols and equations in sentences. Note h is continuous and differentiable for all x since f and g are assumed to be. Okay? By the chain rule. I'm trying to use the constant function theorem. I'm trying to get the derivative here. Let's go ahead and finish the proof here. Now h prime of x, I need the chain rule here, right? Because with each term, there's an inside function and an outside function. This is kind of similar to that related rates problem in that sense. Differentiate f of x quantity squared. It's going to give me 2 times f of x to the first power times by the chain rule f prime of x. And then minus the derivative of g of x squared is going to be minus g of x times g prime of x. Okay, that's what you would get with the chain rule. What do you do now? We want to show this is 0. How? Well, okay, light bulb should go off. Oh, I need to use my assumptions. This is true for all x. That's worth mentioning. By the assumptions that we're making here, I can then say h prime of x equals, replace f prime of x with g of x, 2 times f of x times g of x, and replace g prime of x with f of x. These two functions are very special. They have those properties. Replace g prime of x, g prime of x with f of x. And multiplication is cumulative. F of x times g of x equals g of x times f of x. This equals 0 for all x, and that's a must to emphasize. It's true for all x. Okay? So h prime has a derivative. H has a derivative that's always 0. That means we can now apply the constant function theorem. Therefore, by the constant function theorem, or the constant function theorem implies, function theorem, I'm abbreviating here, h of x equals some constant for all x for some constant c. I could also say there exists a constant c where this is true for all x. But what is the constant? We're trying to show it's 1. That's where these assumptions come into play, and the formula for h again. But by the assumptions, h of 0, you know the values of these functions at 0, is f of 0 squared minus g of 0 squared. F of 0 is assumed to be 1, g of 0 is assumed to be 0. This is 1 squared minus 0 squared is 1 minus 0 is 1. So since the value at 0 is 1, the c must be 1. Therefore, c equals 1, and h of x equals 1 for all x. And we're done. Get all happy and start speaking Latin. QED, quod erat demonstrandum, means I demonstrated what I wanted to demonstrate. I'm done. If you believe in God, you can say praise the Lord, or sometimes people put boxes or shaded boxes or / or various kinds of things, maybe happy faces, hearts, whatever you want to put at the end of a proof to celebrate that you're done, and also celebrate the end of this video. Thanks for watching.